Hello and welcome to Biophysical Chemistry. My name is Umar Aftab and today I'll be talking about problem 6.39 from the Atkins text. And this problem asks us to make an appropriate Arrhenius plot for the following data for the binding of an inhibitor to the enzyme carbonic anhydrase, and it also asks us to calculate the activation energy for this reaction. And so I think that what may be helpful would be to write out the Arrhenius expression and discuss that conceptually before we move on to the question. And so that's written as follows. And so K here is going to be our rate constant. A here is going to be our pre-exponential factor, and we'll get into that in a little bit. EA here is our activation energy, which we're going to be solving for in the second component of this problem. R is the ideal gas constant. And T is our temperature in Kelvin. And so functionally, I think this is important for displaying the relationship between temperature and the rate constant. In fact, that's probably the most important thing about the Arrhenius plot. And specifically, the Swedish chemist Svante Arrhenius, who developed this, what he discovered was that if you take the natural log of the rate constant and you take the inverse of the absolute temperature, then you get a linear correlation. And that's precisely what we're going to be doing for this Arrhenius plot. So what we're going to want to do is we're going to take the natural log of K and the inverse of the absolute temperature. And conveniently, all these values given in this table here help us find that. And so what may be helpful for you here would be to use some sort of software like Google Sheets or Microsoft Excel or Numbers on Apple and open up an Excel sheet or spreadsheet and go ahead and plot all of your values. And then for the natural log of K and the inverse of T. And so for the inverse of T, all you're going to have to do is take 1 over 289, 1 over 293, 1 over 298, etc. And those will get you your values there. And then you can just take out your calculator and calculate the natural log of each of these components. Just note that, as we see here, it's times 10 to the 6th. So type in your calculator 1.04 times 10 to the 6th, etc. and take the natural log of that. And those will be your values. And so I went ahead and already plotted them here, as we can see. So this is what was given to us in the problem. And so these are all the values here that were provided in the problem itself in the table above. And this is what I plotted. So here we have our inverse of the absolute temperature right over here. And this is going to be our x-axis on our Arrhenius plot. And then we have the natural log of K over here and all the values that correlate with that. That's going to be our y-axis on our Arrhenius plot. And so now what's really helpful about using something like Excel or Google Sheets is you can just select both of these columns over here and you can just create an XY scatter plot out of that. And that will help you, that'll essentially make your whole graph for you. So I went ahead and kind of hand drew what my graph would look like, and this is what yours should look like too. And so notice that we have the natural log of K on the y-axis, and we have the inverse of the absolute temperature on the x-axis. And also note this stark negative correlation. This isn't by accident because the slope is actually going to be equal to negative EA over R. So that's negative activation energy over R, the gas constant. And so here, this Arrhenius plot, that was the first component that they asked us to solve for. So now let's move on to finding the activation energy. And so note that the first component to do this part will be to find the slope. And I think it's important to kind of look back at this equation over here and note that we can also write it out in a linear y equals mx plus b like expression. And that can be done as follows. And so here we can see this will be our y, this is our b, this is our m, and this is our x. So just like your typical y equals mx plus b plot. And so looking back here now, how would we find our slope? Well, you may or may not remember from your high school algebra class, but the way you would do this is essentially using the equation y2 minus y1 over x2 minus x1. And so here we can take pretty much any of these any of these points from our x and y axes and plug them into this equation. So I selected these two over here, and I'll plug them in my calculator right now. And the number I got was, oops. And so this is the value I got from my slope. And so luckily for us, there's a direct correlation between the slope and the activation energy necessary for a problem. And so this can be shown by the expression activation energy equals negative r times slope. So we already have our slope over here. And don't forget the negative because your activation energy is going to be positive most likely. And so our ideal gas constant is 8.314. And that's going to get us our activation energy. So we're just going to multiply that in our calculator. And our activation energy is equal to 29476 joules. Joules per mole, excuse me. And so if you're still struggling with this concept, there's a really nice example problem 6.2 in the Atkins textbook. In case you don't have it, I have a picture of it in this video over here, and we essentially have the same exact kind of problem. We have a very similar table given right over here, and here we're asked to find, again, the activation energy, and this time the pre-exponential factor as well. And so the way we would do this is, again, we would take the inverse of our absolute temperature, and we take the natural log of our K, and we put that into an XY scatter plot, as shown right over here. And again, we have a negative slope as expected, right? Because our activation energy has to be positive. And so again, the equation we just used to find the activation energy is shown over here, and the values are just plugged in for, and the activation energy for this specific problem is going to be 91.5 kilojoules a mole. And now if you wanted to find the pre-exponential factor on top of that, what you would do is you would plug that back into the original equation and simply just plug in an x and plug in a y and solve for a. Thank you. And I hope this was helpful.